इस जाकूजी का लग रहा है ज्यादा है इसका।
It's only a dream when your back hits the ground and things turn around you. No, it was only a dream. 'Cause nothing is as bad as you think. Even when you're pulling at the seams, when the lights go out, you still got me. Oh, 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 oh. Detours lead to barricades, and home is for your friends are fake. I'll be there clear. Oh, 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 oh. You know my love can hold you down. You know my love can hold you down. And you know my love can hold you down. You know my love can.
Good morning, Varma sir. Sneha madam.
अमोल सर।
हाँ मैडम, स्टॉप करून दो प्रेजेंटेशन.
हाँ ओके.
हरिवर्मा सर, गुड मॉर्निंग. You are not audible, sir.
Yeah, hello. Is it now audible?
Good morning, sir.
Good morning.
Yes, sir.
Good
Yes,
morning.
sir.
Yeah. So is this Amol?
Yes, sir. I am Amul.
Hello, Amol. Yeah.
We'll start in few minutes, sir.
Yeah, sure.
Over to you, Milin, sir.
Thank you, Amol sir. Is my screen visible, sir?
No sir. Milin sir, your screen is not visible.
हाँ 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 मैं क्या करूँ? Good morning, one and all present here. We are starting our second day. First session of the second day. I welcome Professor Hari Varma. He is working as assistant professor in Department of Biosciences and Bioengineering, Institute of Indian Institute of Technology, Bombay. The topic he will be covering is biomedical image reconstruction. So I am privileged to welcome him. So I would like to introduce him to all of you. He has completed his MSc Engineering and PhD from IISc Bangalore. He was postdoctoral fellow in 2010 to 11, working on inverse problem research, working in inverse problem research group, Department of Mathematics, Aalto University. He was also postdoctoral fellow during 2012 to 15 in Medical Optics Group, Institute of Photonics Science, Barcelona, Spain. His research areas, some of the research interests are as follows: developing novel optical tools for medical imaging applications, laser speckle contrast imaging, and diffuse correlation spectroscopy or tomography for particularly blood flow measurements. He has also worked on inverse problem in medical imaging, which is the topic today he will be covering, theoretical and computational aspects of diffuse optical tomography. Earlier career research award he by D.E.S.T in 2016. He has also got a fellowship by Department of Biotechnology in 2014, Ramalinga Swami Re-Entry Fellowship. So with this brief introduction, I would like to welcome Dr. Hari Varma for his session. Over to you, Hari Varma, sir.
Yeah. So thanks to Professor Deshpande. So I hope you can hear me, right? Hello?
Yes, sir, you are audible.
Yeah, fine. Okay, so thank you for the introduction. I'll start sharing my slides.
Yes, sir.
1 minute. So is it visible? PowerPoint?
Yes, sir.
Okay, 1 minute. Okay, fine. I will close my camera. See. So now it's in the full screen. You can see, right?
Yes, sir.
Okay, fine. Yeah. So the title of the talk is slightly different. So this is quantitative methods in medical imaging. Hello.
You are audible, sir.
Yeah, some echo is happening. That's why.
Okay, I will mute myself.
Okay, fine. Is it clear now?
Yes, sir, it's clear. You can go ahead.
Okay, fine. Title of the talk is quantitative methods in medical imaging. So the idea is that this medical imaging involves both the instrumentation as well as some computational methods to actually create the images. So that's why I took how to actually do this. This imaging. There are some quantitative aspects to it. So my stress will be more on the computational part. The instrumentation will be less stressed. So quickly I will tell you. So I'm Hari. I'm an assistant professor in Department of Biosciences and Bioengineering at IIT Bombay. So my lab name is Theoretical and Experimental Bioimaging. As the name suggests, we do both theory and experiment related to bioimaging. Although I call it bioimaging, most of my work are related to medical imaging, or what you call it, in vivo imaging. So let me start with the problem. So you know this, there are different imaging modalities, right? So you have CT scan, ultrasound, MRI, photoacoustics, PET scan, OCT, fluorescence imaging. So there are different types of imaging modalities, and learning these imaging modalities, or even teaching them to a group of students as a part of a biomedical engineering course, is quite difficult. The reason is, if you look at the physics of CT scan, it's entirely different from the physics of MRI, and so does the instrumentation involved, right? So you know that ultrasound physics is different from the PET scan or the OCT. Photoacoustic imaging has got some other set of principles. The instrumentation is completely different. Now the question is, and the physiological properties that they look for, they are also different, right? So the question is, how do you put all these things into one umbrella and teach the students, or learn, as far as from the perspective of a student, how to learn these things, right? So this is a problem. So as I pointed out here, the different imaging modalities have different principles, and their instrumentation is different. So we should look a way to do this, to teach it in a better way, or to learn it in a better way, right? So one way to look at it is to go to search for a common platform. Is there any common theory, or is there any common concept based on which I can look into all these imaging modalities, right? So that's a approach that I usually take for this type of course, or even if I want to take this field of research, and I'm a newcomer and I don't know which one I should start, or I want to get an overall idea about the whole subject. So what I would do is to look for a common theory, and if I learn that theory, it's like an entry ticket to any of these imaging modalities. Okay, so I know the basics of each and every one, and now I can go and concentrate on one, right? So that is the approach that I'm going to do. So for that matter, let's look at what are called the images, right? So it's basically it's imaging. So let's start with what is imaging, and what are images. So you can see in this picture, there is a bird sitting in a pole, right? And in the background you can see the sunlight, right? Now there are three different things you can see it in this picture, or involved in the background of this picture. Is that one is the light source, right? So there is a source of electromagnetic wave, which is the light that is coming from the sun, and then the pole and the bird is sitting on it. So there is a subject, right? So the light from the sun is interacting with the bird and the pole, right? So the subject is being the pole and the bird. And then after the interaction, the light is falling on your eye or on your camera. So here in this case, the camera, right? So you have got three things. One is the source of some electromagnetic wave. Here is light, and then you have the subject, and then comes the detector, which can be eyes, or it can be your camera, right? So these are the three things that we have. Now, how does it work? So the light from the sun or the source interacts with the object. So in this case, it casts a shadow, right? What is a shadow? It's a variation in intensity, right? So the light being blocked by the bird and the pole, the rest of the light falls on your camera. It creates a contrast, and that is being recorded, right? So in case of eyes, what it do? It actually records this, sent to the brain, and the brain do a post processing. And from your previous experience, you know that this is a bird sitting in the pole, right? So you have learned it. So it actually do a comparison with the early the information that you have collected from your earlier learning experience, and then it do a comparison, and then tells you that, okay, this is a bird sitting in a pole, right? So these are the things. So basically, you have got a source, you have got a subject, and the probing wave probing wave coming from the source interacts with the subject, and data is being collected by a sensor, and then it is fed for post processing, and that gives you an image which can be interpreted, right? So here we have got both imaging as well as some image, which is the data, and then it has to be processed. In our case, it is the moment you see this in my screen, you know that it's a bird, right? So that is a processing that has happened, right? So if you put it together, so the idea is that it need not always be images. So for example, if you look at the bottom right corner, we can see the dull lake. And again, well, what do you mean by this image? This image means the sunlight is hitting each and every object in this image, and the scattered or absorbed or reflected light is being captured by my camera, and that creates this image, right? So it need not always be the light. Sometimes it can be thermal images like the one in the top corner, right? Or it can be the images of this proton density or T1 or T2 relaxation uh, distribution of the tissue as given in MRI, right? So the images need not always be the visual images that we have using our eyes or using a camera, but it can be some other property. So it's like a you have got some numbers of a property in a three-dimensional environment. So for example, from human head, or it can be from thyroid, or it can be from breast or liver, whatever it may be, some numbers, right, which has got some physical significance, physiological significance, and you put it together to form some sort of a visualization of it, right? So that can be an image. So it need not always be a, what do you say, a visual image, or like what we see. So the idea is that if you put all these concepts together, what we have is a probing wave. Example can be, if you look at the medical imaging systems, it can be an electromagnetic wave, or it can be an ultrasound. And this wave will interact with the object, and the object can be humans, animals, or some biological um, things like bacteria cells, or it can be materials, right? So it interacts with the object, and then the interacted image data will be collected using some appropriate detectors matching to the probing wave. For example, if I use an ultrasound, I have to put an ultrasound detector. If it is light, you have to put an optical detector, and then this data is being either it directly gives you an image, or you have to do some process to get an image. We will come to that later, right? So these are the building blocks with which we are going to see this problem. So the idea is that we are trying to get a common platform. As I told you, there are different imaging modalities, and I want to see them from one common platform. That's the idea, right? So that's in that direction only we are moving. So we have the first concept is that you look at this interaction in a more general way, like as I depicted in this block diagram, right? Now you can see this electromagnetic spectrum. So all of you know this. So there are different types of electromagnetic waves, and each of them have been utilized for this medical imaging purpose. So if you look at the radio waves, people have used it for MRI. Microwave imaging is already there. Infrared. So if you look at the near infrared region, there is a near infrared spectroscopy, because the near infrared light can penetrate deep into tissue. So the visible light is used in microscopy. Then X-rays, of course, computer tomography that you know, right? So depending on different imaging, different electromagnetic waves, we have different types of imaging modalities, and there are pros and cons for each of them, right? So X-ray, if I use, the main problem is that it's an ionizing radiation, so it's not very recommendable to use it regularly. But at the same time, near infrared uses light, which is completely safe. You can use it for longitudinal studies, right? So there are pros and cons for all of this, and there are the resolutions and what are the physiological parameters that we look are all different, right? Now again, so keeping this in mind, the electromagnetic spectrum, let's move on to an experiment where I'm going to give you a black object as depicted here. So this is a black box, and you're told that there is a hidden object inside this black box. Now the question is, can you find this hidden object without what do you say, forcefully opening the box, right? You cannot just do a destructive testing, say for example, what they call it, or invasive. In the context of medical imaging, they call it invasive. So you cannot do an invasive checking or destructive checking. You have to do it in a non-destructive or a non-invasive way. You have to tell me what is inside this black box, right? So if I give you this, the first temptation will be what? So you will first try to look at it, right? So the idea is that when you try to look at it, what happens is the light from the ambience falls on this object, and it will reflect, or it may slightly go inside and come out, and that's your expectation is, and then it will fall on your eye, and with that you are going to see whether you can see something inside. That's the whole process of looking at it, right? Suppose you cannot do that, the next temptation will be to shake it, right? So basically you are trying to measure the sound, right? Or you can have a weigh, right? You can just use the gravity, just have a sense of weight. You don't have to weigh it, but you can have a sense of weight using your sense organs, right? Basically your touch will help you to sense it, right? Or you can even sometimes you can even smell and see with something with some fragrance or something like that, right? So these are basically what we do is we are basically using the what do you say, the electromagnetic waves like light or the sound, right? And then trying to these waves will interact with the object, and then we will try to measure it using the sense organs that we have. So we have again the same three blocks. One is the source of a probing wave, and then you have the object with which the probing wave interacts, and then you have the sensors, which is your sensory organs, and then you try to predict what is inside, right? So this is a common. So this is something which we do in a regular basis, right? But then this is exactly what this medical imaging do, but in a sophisticated way, right? So let's have a look at this common theory. This is what I have depicted here, whatever I have explained right now. So there's a probing wave which interacts with the object, and the data is being collected by some appropriate detectors, and the image of the object property is being looked upon, right? So if you divide, in order to have a common theory, let's look at three definitions. One is the forward model or the forward problem, measurement model, and inverse model or the inverse problem, right? Hello?
Yes, sir.
Yeah, so it's a bit difficult to get the feedback from the audience. So I just want to know.
Yes, sir. Some of them
Yeah.
are commenting.
Yeah. Oh, okay. I am in the full screen, so I cannot see the comments. Maybe I will answer it at the end. So
No,
am I going fast?
no, sir. It's absolutely fine.
Fine, perfect. Okay. So let's look at what are these forward model or the forward problem, measurement model, and the inverse model or the inverse problem, right? So what is forward model? A forward model is something which tells how this probing wave interacts with the object. So for example, if I take a light and I take a piece of, say for example, it's an in vitro imaging where I take a piece of tissue and I am shining it with the light. Now the first question I have to ask is how this light is going to interact with this piece of tissue. So that has to be answered. So unless we answer that, we won't be able to quantify the imaging, right? So this question, how this probing wave interacts with the tissue, is what is called a forward model. So for example, I can you all know that how this X-rays interacts with the tissue, right? So this is basically the Beer-Lambert's law. We will come to that one. So basically, it's a Beer-Lambert's law. It tells you that how X-rays is getting absorbed in the tissue, right? So that is a forward model, for example. Or in case of in case of light in a weakly scattering medium, this is a Maxwell's equation or the wave equation, or the radial counterpart, which is a Helmholtz equation, which acts as a forward model, right? So again, in ultrasound, how the ultrasound interacts with the tissue, like ultrasound scans that we do in hospitals, how this ultrasound interacts with the tissue. Again, it's a wave equation, right? So these are the mathematical models, or the physical, the mathematical models developed using the physical principles. They act as the forward model. So the idea is that, suppose I know the object very well. That means the object properties I know very well. If I know the object properties well, and if I know what is the probing wave I am using, then with the help of forward model, I can generate the data by myself without actually doing the experiment. So what I do, I will simulate a wave, probing wave, then I will feed it into the forward model that is implemented in the computer, because it actually mimics the object, right? And this forward model, which is an equation, will be solved, and it will generate some data, and that data will be actually my experimental data. It's a simulated data, but it should match to the experimental data, because this is a forward model for this particular object interacting with that particular probing wave, right? So you can view it like that. So this is we can avoid doing experiments if you have a forward model, because it actually tells you what is the mechanism with which the probing wave interacts with the object. Now comes the measurement model. Now, as you know, then I say, for example, if you take the light, right? So what are the quantities that I can measure? I can measure the amplitude, I can measure the phase, I can measure the polarization if you want. I can view it in the Fourier spectrum. Instead of time domain, let's go to Fourier domain and measure some spectrum of the signal, right? So there are different measurements associated with the signal, right? I can autocorrelate it if you are looking for some statistical properties. So there are several things that I can derive from the measurement. So the measurement model depends on what are we actually measuring. And the third comes the most important thing as far as we are concerned, which is the imaging problem. So what is imaging problem? The imaging problem is, as I told you, the probing wave is going to interact with the object. Now it has got a mathematical equation. That equation will tell you how this wave is going to interact with the object. Now there are some object properties which actually comes in this equation, right? So for example, if the X-ray is being illuminated to a tissue, the X-ray absorption coefficient will come into action, right? Because the X-ray is being absorbed, and the absorption coefficient depends on the tissue, right? Each part of the tissue may have different absorption coefficient, right? So in that equation, in the Beer-Lambert's law, you will get absorption coefficient as a parameter, right? So what is my aim? I want to extract that parameter. I want to plot that parameter in a three-dimensional environment, and that is my image, right? So if it is an X-ray imaging, I am looking at the absorption coefficient distribution in as a three-dimensional plot, and that is my image, because it will give you an idea about the object in an indirect way. So extracting the object property from the measurement given the forward model is called the inverse or the imaging problem. So inverse problem is also called imaging problem, because the idea is that you get the measurement, you should know what is the forward model. With these two, measurement and the forward model, you try to reconstruct the image the object property like an image, and that's why that's called inverse problem or inverse imaging problem or an imaging problem, you can say, right? So let's move on to next few slides. I'll try to relate this to the general, to things that you see in your real life. So these are something like some idea. I'm not going to the details of these problems. These are some of these examples are forced ones. Some of these are natural. So you can decide whether this is an apt example or not. You can think about it by yourself. I'm not going to explain any of these things. Basically, I'm going to throw some questions to you and see whether you can think about it, right? So for example, let's look at these concepts, the forward and inverse problem from these images. So this is you can see when the ducks float in the water, it actually leaves behind the trail, right? Water trail. Now you can see that depending on the some ambient conditions like wind and all those things, the question is whether the trail that create by a particular duck, will it be unique to that duck? And if that is the case, if by looking at the water trail, can you actually find out which duck produced it? So you try to find yourself what is a forward model and what is inverse model. So let's go to the next image. So you know that each food is associated with a unique aroma, right? But then the question is, can you identify the food from its aroma? I'm sure you guys are doing it. You can still think about a possibility of inverse problems here. So going to the next problem, which is quite problematic in monsoon in Mumbai, there are manholes. I think I should not use that word. Just few days ago, it is banned, right? So anyway, so this manholes creates a lot of problem because the water can go inside. So I mean, it can be opened in the monsoon, and so some people can. I mean, some accidents can happen. Now the question is, can you identify these holes? The idea is that you can, because from your experience, you know there is a turbulence happening around, and you can easily identify it. What happens if it is a very dark? I mean, there is no light in some particular area, and then how do you identify it? Still you can, because from the sound, right? So again, think about the inverse problem associated with this. Similarly, the bat, echolocation by bats. So this is very obvious example. So the bats emanate sound, and the sound will get reflected from some objects nearby. And it is said that the bats can actually infer the shape and the location of the object, right? So there are some papers on this. You can have a look at it. Again, this is an inverse problem. So crossing the road. So if you look at the Indian scenario, where we are very much used to cross the road even without the signal. So we will look at whether the vehicles are approaching, and then we take a decision. Now you look at this problem a bit closer. So what we do when you try to cross the road, of course, not in a zebra line or not in the signal, we are first going to look at the approaching vehicle, right? So what are you doing there? The ambient light reflects from the vehicle, and it falls on your detector, which is your eye, right? And from this, you are going to quantify the velocity of the object. Of course, we are not going to quantify in terms of what is a kilometer per hour or anything like that. What we are basically doing is to have a rough idea about the speed of the vehicle, which we can do, right? So that is being processed in the brain, and then we take a decision whether you want to cross or not, right? So this is something that you can relate to your daily experience. And then crossing the road in a very what do you say, in a junction with a lot of traffic is going to be much difficult, because you have to take a lot of decisions. The vehicles coming from different directions, people are walking, right? So again, there are several inverse problems happening. So we do a lot of inverse problems in daily life, but maybe not in a quantitative way, but still in some sense it's quantitative, because it actually helps you to take decisions. So I consider it as an inverse problem. You can disagree to that, but think about it. Now comes the driving. So for example, driving in a misty day. So the idea is that in roads, so you know from which direction the vehicles will come, approach, or what way they overtake you, and there are pedestrians, right? So there are so many things happening around you, and you have to take a decision based on that. And actually, what is helping you, this forward problem is something which is embedded in your head because of your previous experience. So every time, so for example, when you are driving, some area will be very familiar to you. So what does it mean? So you have been there, you know the geography, it has been fed to your brain, right? So next time when you go there, the measurements is being picked up by the eyes from in a live fashion, and it is fed to the brain, and it interacts with your real forward model, and then you take the decision, right? So that's basically the learning process that we have done, right? So this a priori informations about a geography of a place will always help you, because you have some forward model built in the brain, and then you take the measurements, compare it with your forward model that you already built, and then take a decision. So think about it, whether it makes sense to you. Learning process in children. So there is something really you might have observed. I don't know, your seniors might have observed, like the kids, when you give maybe less than 2-year-old or maybe less than 1-year-old, you try to hide something in front of them. So the idea is, the moment you try to hide, they will start crying, because they don't know the concept of hiding. So you just show them some things like a ball, and then quickly hide it under the pillow in front of them. then the problem is they will never realize that you have kept beneath the pillow. And it takes some time for the brain to learn this process, that the concept of hiding things, right? So can you actually relate this to the inverse problem? Similarly, learning process, right? So basically this kid is looking at the rain, and it is actually learning, okay, something is coming, and the next time when I talk about rain, it will start looking outside, because it knows that I have to look outside to see the rain. So that's a forward model being built, and the next time when I ask, that's a measurement, and it is fed to the brain. It relates the previous experience, which is nothing but the forward model, take a decision, and it will act according to that, right? So that's how the learning process in children, whether you can view it as an inverse problem, you think about it. Then there are in music, right? So there are many, even the film music being composed based on ragas, right? So there are many Carnatic ragas or North Indian ragas based on which the film music can be composed, right? Now the question is, hearing a film music, can you actually find out the raga, the underlying raga? So is it possible? Or the copy, there are people who actually copy the music tune from some old songs and then try to make new songs. Can you catch those copycats? So these are all inverse problems for me. You decide again. So this is one very bit involved problem. So can one hear the shape of a drum? So this is quite mathematical, although it looks nice. The title looks very, what is relating to us, but then it's a bit more involved than what you think. So this problem was proposed in, I think, in 1966, and it was solved in 92. So the idea is that depending on the shape of the drum, the sound that is coming, basically it's a fundamental frequency and its overtones can be different. Now the question is, by measuring this sound, can you actually infer the shape of the drum? From which drum? Sorry, what is the shape of the drum from which the sound is coming? So that's inverse problem, right? I think the answer is no, but you can have a look at the 90 papers. But just search this, you can find out a clear answer to this. But it requires a bit of more mathematics than you may perhaps have from your bachelor's degree. So sorry, I don't know the audience properly. I hope these are B.Tech students. Am I right?
Sir, I would like to brief you. Almost 86% are faculty from engineering institutes.
Oh, really? Oh, sorry.
Yeah,
okay,
15 to 20% are faculty from biotechnology and pharmacy also.
Okay, fine.
Yes.
Fine. Okay, so I was not knowing that. Okay, fine. Yeah. Okay, thanks. Okay, so then another problem that you can think about is the deblurring. So you can see a photograph in the Poway Lake. So you can see in the background there is a buildings you can see in a misty day. Now the question is, from this photograph, can you actually recreate the actual image of the building without any blurring? So this is called the deblurring problem. So the more the mist on the right side you can see, the less the image, the less the quality of the image, right? So from this image, can you actually recreate or recreate the actual image? And that process is called the deblurring, right? So this is again this is a very classical inverse problem. I mean, it is identified as an inverse problem. Similarly, for example, if you look at the background of the Marine Drive, you can see the sun cast a shadow, and you can see a nice shadow of the building here. Now, the question is, from this, can you actually build a three-dimensional image of this building? So you think about it, if possible or not. Again, coming back to this problem, so if you look at it, if you have noticed while you're traveling in car during a rainy day, the outside images will get distorted because of the trickling water through the window pane, right? So this you might have, I'm sure you might have observed. Now the question is, can you reconstruct the original image? Say, for example, here the Washi Bridge, looking from the bus. So can you actually recreate the actual bridge from this distorted image? Or another problem I can pose is, given I will give you the actual image of this bridge, and using this particular distorted data, can you infer the velocity of the car? or can you infer the velocity of the rain, or I mean the quantity of the rain in some way? So these are the associated problems that you can think about. Or if you look at this lake, say for example, in a sunny day, you can see the sunlight get reflects and it falls on your eyes, and it almost look like what I've shown you on the river Ganga at Haridwar. You can see that image. And when the wind blows, I'm sure you might have observed when the wind blows, this image will get blurred, right? So the question is, from this blurred image, can you infer the wind velocity? Again, an inverse problem. Think about it. Pulse oximeter. It's a very classical example of inverse problem. So here we are giving a near infrared light. It interacts with the tissue, and then it will give me some scattered data from which I can infer the tissue oxygenation, right? Basically, the light interacts with the oxy and deoxyhemoglobin content, and that data can be used to quantify those oxy and deoxyhemoglobin concentration and then the tissue oxygenation. So this is now quite common in COVID days. So this is a classical example of inverse problems. There is no imaging in many of these things, I agree, but I'm talking about inverse problems. Of course, the X-ray imaging for dental applications is quite obvious. So you can see how the X-ray is passing through the dental, through the teeth, and it can reveal you the cavities, right? And if you want, this is just a projection data. But if you want a tomography, then you have to go for computer tomography, which will give you a 3D image of the object. Again, this is the X-ray absorption coefficient of the teeth, the bone and the enamel and all those associated tissues that is being shown as the image, right? So this is basically, so if you do a cone beam computer tomography, it gives you a three-dimensional distribution of the absorption of the of the tooth, right? So then the non-destructive testing that is employed in airports, where they look for the possible dangerous items in your goods. It's again an inverse problem, imaging problem. Then this is a really nice example, near-infrared spectroscopy for painting. So here the idea is that many artists when they do the drawings, they do a lot of corrections, and most often these corrections happens one above the other. So they give a coating and then correct it, and above that there will be more coating. So the final art will come after so many corrections, and all these corrections you can see one below the other in the work. Now the question is, can you actually reconstruct all these layers? It's possible with near-infrared spectroscopy, because there is no other way to do this. You cannot destruct it and find out what is inside. So the idea is to non-invasively check how an artist work on the a picture, or and then how it involves, how their mind works, and that work actually evolves to the final product. So this can be inferred using near-infrared spectroscopy, right? So think about it. Then forensic crime scene reconstruction. So if an investigator, when they go to a crime scene, they try to collect all the evidences, right? It can be chemical, it can be some fingerprints, many of them, and then put it together and try to recreate the crime scene. So it's clearly an inverse problem. Or a police dog which do sniffing, right? So basically, the sniffer dogs have a training. What is the training? It has to sniff different objects and identify those objects. So basically, it is building the forward model in its head, right? And after some time, when it is taken to a crime scene, it will sniff, and that is a measurement. That measurement is fed to his brain, and it will match with the forward model which it has already got while training, and then it compares and tells you what is happening, right? What material is it? Or it can trace the criminal or other objects, right? So that is how we do. So there is a forward model which it got during the training period, and the measurement is taken from the crime scene. Comparison is done in the brain, and it take decision. Again, an inverse problem, right? So putting it together, the imaging system, you can consider it as a probing wave, a subject, and the measurement. The probing wave can be ultrasound, it can be light, right? X-rays, anything. then you can think about so many things about it, whether it's you have to illuminate the object uniformly or it should be focused, what wavelength I should I use a normal light or should I use a laser? That means should I think about the coherence? Should it be continuous pulsed or it should be modulated? So these are the questions that I can ask about probing wave, right? And then the subject can be humans, animals, materials. Again, it depends on what you want to look at. And the detection. So detection, again, you have to select based on the probing wave. If you are using a light, you have to use a light detector. If it is an ultrasound detector. Even if it is light, which wavelength do matter? So if I am using a light at 683 nanometer, then I have to put a measurement system which is sensitive to 683 nanometer light, right? So all these considerations you have to look at, right? So these are the things that you have to think about when you look at an imaging system. So this is some example where we actually do an imaging inside a lab. So you can see that a mice brain, you remove the scalp and illuminate it with a laser source, and the scattered data is being picked up by a camera, and you can see on the right side the image. And on the lower part of the image, you can see it's like a noise that you might have seen in your old television sets, like a I don't know the. So this particular noise is useless if it looks like this, but the moment you do compute something called a speckle contrast, you can see that it actually reveals you some information about the brain. So basically it is proportional to the blood flow. So you can actually see the blood vessels, right? So although the raw measurement appears to be noisy, the moment you do some statistics, or the moment you do some post-processing, you can reveal the blood vessels, or you can extract the information. So this is a classical example where we do an imaging and then an image processing to extract useful information. This is again an inverse problem. So now we will see how this probing wave interacts with the tissue in a very general way. So you can see that X-rays, for that matter, when it passes through tissue, it actually goes in a straight line, whereas this light, it gets scatters, right? So if the X-rays are going in a straight line, because the energy associated with the X-rays are too high, so it is not going to scatter in tissue. So the idea is that the forward models associated with X-rays are pretty simple, because it is going in a straight line. You don't have to worry about any other directions. That we will see why is it so. But the moment light comes, it actually scatters. So the intensity is going to change in all XYZ directions, and that is going to create a lot of problems. So the forward model associated with the light is going to be complicated. But then light is safe. So what is the trade-off? That's the mathematics associated with the light is complicated, but it's safe to use. But for X-rays, the mathematics involved is less complicated, but it is not safe to use. So there is always a trade-off between what these imaging modalities offers to you. So you have to appropriately select one that suits you, right? You cannot say one is better than other. There are pros and cons for all of them. So let's look at some experiments very quickly. So I've got a beaker, and you can see two images in one. So this black rod acts as an inhomogeneity in the sense that you can consider this white beaker as something like a healthy tissue, and this black rod as some sort of, let's say, for example, a tumor, right? So my aim is to find whether this healthy tissue has a tumor or not. Suppose my tissue is transparent, then I can easily look at it and tell, okay, there is a tumor. That this is actually depicted on the right side figure, where a glass of water acts as a transparent medium. So if the tissue is like that, you don't need imaging. You can just look at it and tell it, right? Why? Because the ambient light is not getting scattered or absorbed by this water. So it just hit this object and reflects back, and that is being picked up by eyes, and I know that there is a problem inside this, right? But the tissue doesn't act like this. Tissue has got scattering and absorption, like depicted on the left side, like a milk. So it's like a milk droplets add to this water, so it acts as a scatterer and absorber. So you can see that you can no longer see this rod. So you are not sure whether such a rod exists inside. Of course, forget the top part. So if you look at a cross section from the below, you don't know whether there's such a rod exists or not, right? So that's a problem. So what you have to do is, can we put some extra? Can you extract some information by putting some probing wave? That is what you are going to look at. So in this figure, you can see I'm going to put a laser source. So first, let's have a look at the behavior of this laser source in such an absorbing medium. So suppose this water doesn't have much absorption. So you can see the laser source will go in a straight line. So I can assume that the absorption is negligible and the scattering is also negligible. You cannot say that scattering is zero because I'm seeing it from the other side. If this is exactly going in a straight line, I won't be able to take a photograph from this side, because some light has to fall on my detector, and that's why I'm able to get this light. That means there is scattering, but the scattering is much less. That's why I can more or less see it as in a straight line. Now what happens when I put some ink to it? So I'm dropping some this writing ink to this one. Then you can see the light is getting absorbed. So you can see it is not reaching from the right to the left. It got absorbed almost in the middle, right? Now what happens if I put some milk as well? So I'm going to add more milk. That means I'm going to add more scattering. So now you can see that there is no more straight line, because now it has got a spread. It is not in a straight line. It has got spread, and it is also getting absorbed because it is not reaching much to the left. So this is the scenario. This is how the light behaves qualitatively in tissue. It gets absorbed and it gets scattered. Now the question is, how do you model this? So anyway, before going to that, we can have a look at our old problem, which is, that means looking at a rod. So if you look at, so I'm going to put a rod here, and this acts as my inhomogeneity, like a physiological condition. Now I'm going to put a laser again. So if I put this laser, if the light is not in the path of this object, it will just pass. But the moment it is in the path of the object, that is being blocked, or it can just if it is not a opaque object, it can just reduce the intensity, or it can scatter the intensity, and something will be picked up by the camera. Now the question is, given the forward model, that means how this light interacts with this particular material, that means a beaker with water and a scattering object, and the measurement, that means picked up by this camera, can you infer the presence of an opaque of an inhomogeneity, like an object like this inside this tissue, inside this object? That's the idea of imaging. Now can you relate this to a real life example where you can see the water? So when the water is flowing, the water wavefront will be distorted by the presence of a stone. Now, by measuring this distorted wave, can you infer something about the water velocity or the shape of the stone? So think about it. So this is something like that, if you want to relate to your real life examples. So the idea here is, you take this measurement, and suppose I know the forward model, how the light interacts with this material. Then what you have to do is to take this measurement and generate a data corresponding to the case where we don't know the inhomogeneity. That is what I have put it in the computer. I don't know the inhomogeneity. I want to find it. So what I do is, I will take them, generate a forward data using my forward model, and that will be compared against the measurement. Clearly, these two measurements, one the actual measurement, another is the simulated measurements, they will not be equal, because we don't know the actual inhomogeneity. So whatever data we have generated on the computer will be different from whatever data that you have from the actual measurement. So this difference will be proportional to the type of the inhomogeneity that is being embedded in the object. So that can be reconstructed using some appropriate inverse model. So that will be done in the computer. So this is a general scenario in which we do the imaging. So again, coming back, it's a recap. So forward model tells you how the probing wave interacts with the tissue. Then comes a measurement model. As I told you, it can be different. And then comes the inversion algorithm. That means use the measurement and the forward model and try to reconstruct the object property or the tissue property. So let's go to quickly to, let me see if I'm, okay, 10:54. So let's quickly go to the case of X-rays. So suppose we are looking at the X-rays, right? So you know that it's Beer-Lambert's law. What does it tell? It tells you that the rate of change of intensity variation, right? Di by dx is proportional to the local intensity and also to the distance traveled. And the proportionality constant is absorption coefficient. So this is a first order differential equation, and the solution is nothing but I is equal to I0 e raised to minus mu z. Right? So this is the Beer-Lambert's law. I just want to stress the fact that as the X-ray is going in a straight line, the differential equation, the model, the forward model is a first order differential equation, and the solution is what we are looking at. We call it as a Beer-Lambert's law, which is I is equal to I 0 e raised to minus mu z, right? That is being depicted here. And you can see if there are 4 of them, say mu1, mu2, mu3, and mu4, you can just add all of them in the discrete sense. But if it is continuously varying, that means mu is absorption coefficient is not constant, you can take an integral. So you can have I 0 is equal to II e raised to minus integral mu of x dx. And this acts as a forward model. What does it tells you? An object with an absorption coefficient which is varying inside an object. Suppose the input intensity is II, the output intensity is related to the input intensity and the absorption coefficient using this relation. That's what it tells you. And the underlying equation is a first order differential equation. Why? The differential has to be taken only in one variable because the X-ray do not scatter. It just go in a straight line. So you don't have to worry about any other dimensions, right? Any other differentials in any other directions. Now we define a data, what is called projection data, P theta of t, which is log e to the base II by IO. And that is equal to the integral mu of x dx. That means this is the projection data that I am going to look at. Now, you can see that if you again do a discretized version with the 2 absorption coefficients, you can see that you cannot use just one angle. Say, for example, if I am using one measurement, I will get 2 unknowns in and 1 equation, because the data is log e to the base II by IO, which is given to you because you can measure it. Unknowns are mu1 and mu2, right? So there is 2 unknowns and 1 equation. So you cannot solve it. So you need to generate more equations. So how do you generate more equations? So you can see that you cannot generate more equations by changing the input power. That is not going to happen because the measurement is II by IO. So the moment I change II, IO will also change, so that II by IO will remain constant. So you cannot generate more data by changing the power, but you can change it only if you change the angle. And that's the importance of angle in X-ray CT, right? So that is depicted here. So in order to generate more equations, because the unknowns are 2, you have to get one more equation. So you have to illuminate the object in a different direction. So first we put it at theta equal to 0. Now you take theta not equal to 0, 1 measurement, and these 2 equations can help you to solve mu1 and mu2. And this can be extended to any case. So this will tell you why do you need data from different angles, right? Now this is another problem. Here you can see the intensity II. In one case, the intensity is just not touching the region with inhomogeneity, where mu not equal to 0, whereas one ray is actually touching it. Now the question is, we don't know exactly where this region is, where the inhomogeneity is. So which ray I should use? I don't know. So in that case, I have to put so many X-rays in parallel. And that's why we need to illuminate the object with different rays. So this will tell you 2 things. One is theta, because we have to get information from different angles. And then we should have different parallel lines. And that is depicted by t. So with these 2, we have the projection data, which is P theta of t. And this is being depicted here. Each X-ray is going, and it actually, what does it do? When it goes through the straight line, at each and every point, the absorption coefficient reduces intensity, and that data is picked up as P theta of t for a given theta and for a given line or a given ray. And that is my information. Now, what is the forward model? Forward model is the Beer-Lambert's law. What is the inverse model? So measurement model, which is P theta of t, defined as log II by I0, which is nothing but the integral of the absorption coefficient along this line. And what is the inverse model? Inverse problem is, given the measurement model and the forward model, find mu. That means the X-ray absorption coefficient, right? So the object property has to be found, which is mu, given the measurement and this forward model. And that's what being done in X-ray computed tomography. Now, let me go through this one. So the idea is that I think I'll just go quickly. So the most important thing in this case is the Fourier slice theorem, which tells you that this particular thing can be done. Suppose I have the Fourier P theta of t, which is my projection data. What I can do is I can take the Fourier transform of this. So if I take the one-dimensional Fourier transform of this one, which I denote it as S theta of omega, then there is this theorem tells you that the one-dimensional Fourier transform of the projection data is equal to the two-dimensional Fourier transform of the object restricted to the line. So you can see that, suppose I am taking the measurement p theta of t for a given theta, you take the Fourier transform that is equal to the Fourier transform of the object as restricted to a line which is again inclined at theta, but in the Fourier space. So what you have to do is, you suppose you know the object, you take the two-dimensional Fourier transform of it, then I can plot it in the Fourier domain, right? Now the question is, here is, I don't know mu, but I know p theta of t because that is a measurement that I have. You take the Fourier transform and fill your Fourier space of the object. So what happens is, we are going to get data in these radial lines as I shown here. So for every radial line you are going to get a lot of data. Now the question is, I have got the Fourier transform of the object that I am looking for. Now how do you find the object? You take the inverse Fourier transform. So that's how the Fourier slice theorem do. The Fourier slice theorem helps you to do that. So what we can do is, you first get this data in all these radial lines, interpolate it to a rectangular grid, and take the inverse Fourier transform. That will give me the object directly, and that is how the CT computer tomography works. So if you look at here, so there are some images here. You can see that the left side is the original object and right side is the reconstructed object. So I have done this exactly the same thing. You take a lot of projection data, take the one-dimensional Fourier transform, use the Fourier slice theorem to get the Fourier transform of the object, and then interpolate it, and then take an inverse Fourier transform. That will give me this image. And you can see that there is blurring. And why this blurring happens, I will tell you. Right? So now another option. So this is there are problems with this type of imaging, because as I told you, as you go away for higher frequency, that means larger U and larger V, the data is going to be coarser because it is in radial lines. The data acquisition is in radial lines, along radial lines. So the data that you are going to get at larger frequencies are going to be coarser. So that creates a lot of smoothing, and that's not something recommendable, right? So we are going for what is called simple back projection. So here you can see that an object, suppose I am putting an X-ray, it casts a shadow. You take that shadow and smear it back to the object domain, just like what I have done here. So if I do it for all angles, then you can see something getting reconstructed at the center, which is nothing but this object. So this top figure is now, it's a slice. And if you extend it to a 3-dimension, you can see it can reconstruct the object. So basically what you have to do is, whatever data that you are getting, which is a projection data, you just smear it back to the object domain. Just like what I am doing here, you just take a one rectangle. This is smearing it back along the object domain, and keep doing it for all angle, and then add all of them together. That can create an image. That is called the simple back projection algorithm. And you can see that, I'm skipping the mathematics, and you can see that this can create a blurred version. So you have the original here and this something reconstructed using the simple back projection, and you can see it creates a blurred version. And this is basically because there is a convolution happening, which we can prove that the original image is blurred using because of the function 1/r, and that is because of the radial data acquisition. Because every time you have to rotate and get the data, that is equivalent to getting data along radial lines. That's a problem. So that creates this blurring. And there is a way to avoid it in using what is called filtered back projection, where you can actually remove this 1/r effect by using mod omega filters. I'm not going to the details, but then you can see that I can recreate images which are less blurred. You can compare yourself this one reconstructed by simple back projection and one reconstructed by the filtered back projection. Right. So what the essential idea about the X-ray tomography is that what we have done is, we have got a forward model, and then we associated with that forward model, we found out that the Fourier analysis or Fourier transforms can be a useful tool for it, and we developed a Fourier slice theorem which helped you to do the reconstruction. That's what I have presented here. Now we will see, so this is a case when X-rays are used. That means the ray is traveling in a straight line. So I have actually used some experiments to demonstrate it, because more or less it is going in a straight line, right? The moment the scattering is less, this is going in a straight line. That can actually mimics the case in which an X-ray is actually passing. So the scattering is less, so it's going in a straight line. So that's what we have seen so far. Now we will see what happens when there is a scattering. So that is what is called the diffraction tomography. So the problem with the diffraction tomography is we cannot think about things moving in a straight line. It has to scatter. Now we will see the case where the scattering is not so dominant that the wave phenomenon is again applicable, and that is called the diffraction tomography. And diffraction tomography is something that is used for ultrasound tomography in the olden days. So by diffraction tomography they mean actually ultrasound. um, but ultrasound, ultrasound has is a mechanical wave. It has nothing to do with electromagnetic theory, but still ultrasound, the forward model that is used for ultrasound and the forward model that is used if I am using a light remains the same. So you can see that in the if I am using a light for this particular case, we can derive from the Maxwell's equation, and finally I will get a Helmholtz equation. This acts as a forward model. But at the same time, if I use an ultrasound, I can use the basics of continuum mechanics, and then I can see that that will also will give you the same Helmholtz type equation. But of course, the functions associated with them have different physical meaning, but the structure remains the same. So the idea is that, again, you have to think about the common theory I was talking in the earlier slides. So we have to look at that even though they are seemingly different physical principles, the underlying max remains the same, right? So any theory that you develop here for ultrasound or the light, in case of weak scattering, is going to be the same because the structure remains the same. Now here, what is the forward model? I'm going to put a light to a scattering medium, and now we have to look at the object property, which is a refractive index, and this light is going to get distorted by this refractive index, and from the distorted wave, can you infer the refractive index? And the refractive index can be a measure of physiological property of the material that you have. So this diffraction tomography is basically used for cell imaging, in vitro applications, because in vivo means the light is not going to get these diffraction models are not going to be applicable if I am going to put a light into tissue, because the scattering is very dominant. So this particular problem will not be fit. But it can be used for the cases of in vitro imaging, where cell imaging can be done, where there is not much scattering. These models are going to be applicable. So again, so let me skip this. So here you can see how a plane wave is getting distorted by an object like this. So you can see a left hand side, there is a plane wave. It is moving and it hits an object, and the wave is getting distorted. And from this distorted image, can you infer what is this object? That is the thing that we do in diffraction imaging. So now the question, the point that I want to stress here is, the idea is that as you go from one imaging modality to other imaging modalities, as I told you, there are pros associated with them, but there are cons as well. So let's look at the X-ray computed tomography. The mathematical model is quite simple because the X-ray travel in straight line. So this is as simple as I0 is equal to II e raised to minus integral mu of x dx. And then I want to find mu given IO and II and this forward model. And this is quite simple. You can use the Fourier tools, Fourier domain. You can solve this problem in the Fourier domain. But the problem is X-rays are ionizing, so it's not recommendable to use it often, right? So that is a problem associated with tomography, although the mathematics is quite simple. But then the moment you use light, then the things are different. So if you use an ultrasound or a light in a weakly scattering medium, you are not going to have you have to face scattering, so that you cannot have a simple ordinary differential equations. You have to have partial differential equations, and the mathematics is complicated. So the associated inverse problem is also complicated. They call it what is called ill-post problems. I'm not going to the details, but the problem, it actually means that the imaging is not trivial, right? Then comes another difficulty. So this is weakly scattered medium. So for example, you take a cell and put it under some light and try to reconstruct a three-dimensional structure of the cell. That is a diffraction problem, because the cell is being isolated. There are no surrounding materials which scatter the light. It directly interacts with the cell, so that we will have nice images. But the problem is that is not the case. If you want to do an in vivo imaging, like in medical imaging, you have to have do the imaging without taking anything out, right? So it should be in vivo. So in a non-invasive way. So the idea is that you have to encounter the scattering in such a scenario where the scattering is dominant, but we have what is called the diffuse optics, and then the forward models are complicated. You can see when light actually hits the tissue, in non-invasive in vivo imaging, you are going to have a very complicated integral partial differential equations, and these complications will keep on increasing. If you go to photoacoustics or fluorescence imaging, all these forward models that I mentioned are going to get complicated, right? But then it has got its own advantage. They are safe and all those things are correct, but the scattering spoils everything. So these things you have to keep in mind. So now, how does MRI fits to this? So I don't have time, I guess. So I'll tell you quickly. So the idea is that this MRI is actually related to CT. So as you know, this protons acts as a random tiny magnets, and when it get aligned with a larger field, the moment you flip it using a 90-degree RF pulse, it starts rotating or process in the XY plane, and it induces a signal, right? And by giving a gradient to the main field, I can have what is called the signal equation. This S of t is equal to m of xy and so on. This is actually the two-dimensional Fourier transform of the magnetization of the object. And magnetization will actually give you some idea about the physiological parameters of the tissue, right? So this is basically the signal that you are getting is basically the two-dimensional Fourier transform of the object itself. And if you relate it to the computer tomography, you can see that that is exactly the case, because there the projection data by Fourier slice theorem, the projection data is also related to the Fourier transform of the object. Here also the signal that you are getting is related to the Fourier transform of the object. But the main difference is, if you look at this graph on the left side, you can see that this is a scan that is done using MRI radio frequency signals. But you can see the data acquisition is just like what we do in X-ray CT. That means along radial lines. But that is MRI is not restricted to this this data acquisition. You can see that I can do a raster scanning as well. So I can get the Fourier data in a regular rectangular grid. But for X-ray CT, that is always restricted to radial line. So this is a major difference as far as imaging is concerned. MRI will give you a lot of different choices of scanning, getting the Fourier data. So this particular space is called K-space. So both X-ray CT and MRI works in the same K-space, but the data acquisition in X-ray CT is restricted to radial lines or in the polar coordinates, whereas MRI we can have different types of scanning. That's the power of MRI. So when we learn this or when we teach this particular topic, we can have the same common approach to both X-ray CT and MRI from the signal imaging viewpoint. So moving to an near-infrared spectroscopy, as I told you, the light interacts with the tissue and it gets absorbed at different wavelengths. And you can see that if I do look at the near-infrared region, that means roughly from 633 to 850 or 900 nanometer, you can see the light will be absorbed only by oxy and deoxyhemoglobin of the red blood cells, but it is not much absorbed by water and lipid, so that you can have some information about the tissue. So that's why we select this part. So again, there is multiple scattering inside the tissue, and again comes a forward model, which is nothing but the radiative transfer equation. I'm not going to the details, but then this you can see that this equation is going to be much complicated. So we have to come up with what is called the approximation, which is called the diffusion equation, and that's why we call it diffuse optical imaging, because the light, when it encounters the tissue, it has to go multiple scattering. Multiple scattering means every time it encounters a scatterer, which is the tissue, like oxy and deoxyhemoglobin content of the tissue, it gets scatters. Scatter means it changes the direction. So it keep on changing the direction, so that adopting a wave picture is difficult. So we have to go for what is called the radiative transfer, which is a photon picture. But still this is again complicated, so we go for a diffusion approximation. Again, this is a partial differential equation. There is no ordinary differential equation because the light is scattering. Now the light penetrates, and you can see that this can be utilized to find out the two optical properties of the tissue, namely the optical and optical coefficient, and the optical absorption coefficient and optical scattering coefficient. Right, and then this can be related to the tissue chromophore concentration. So once you get the absorption coefficient, you can relate it to the chromophore concentration. And chromophore here is oxy and deoxyhemoglobin. and then this can be further related to the tissue oxygen saturation, and that is exactly what is done in pulse oximeter. So this is just an FNAR. So I will come to that in my from our example. So here the idea is that, again, coming back to DOT theory, let's look at the forward model and inverse model. So the forward model is how the light interacts with the tissue, which is the diffusion equation, and the parameters of the tissue is optical absorption mu A and optical scattering, which is mu S dash. Now the problem is forward model is, or forward problem is, given this equation you find out phi. But inverse problem or the imaging problem is given phi at the boundary. That means you are measuring only at the boundary, right, of the object. And given the forward model, you find mu A and mu S dash. So again, we can reduce this problem to this type of concepts. So this particular slide actually tells you how to do that. So basically it's a perturbation approach. So if somebody is interested, you can have a lot of literature on this starting from 90s. But maybe you can contact me. I can help you to find out proper literature. So I'll skip these things. So finally, you can see some images. So this is a diffuse optical tomography being done in two-dimensional images, in 2D. So you can see the original object on the right side, and this is a reconstructed one. So this is done in using a finite element method. And you can see the corresponding 3D in FEM. So you can see an original object here and the reconstructed one. And these are the different planes to see how spatial localization is being done. So the main problem with this type of tomography is the resolution is always limited to 1 millimeter. And there is always a problem of reconstructing spatial errors in reconstruction. So it will always get biased to upward if it is in the reflection geometry. These are the problems. But anyway, this do a good job. Now the problem is, some more problems are like what happens if the scatterers actually moves. So far I told you that there are scatterers and the light encounters these scatterers. It can get just scatter, and the scattered data can be utilized to reconstruct the image. Now the problem is what happens if the scatterer moves, like red blood cells, which actually moves, right? Then you can see that intensity actually fluctuates. The light that is being scattered actually fluctuates with respect to time, and this fluctuation contains the movement. So the idea is that you can actually quantify the blood flow, not just the tissue absorption coefficients, but it can actually measure the blood flow as well, using what is called the speckles. These are called the speckles, and there are two different ways. One is using what is called the autocorrelation function. In such a case, the imaging modality is called diffuse correlation spectroscopy, and another is the speckle contrast. In such case, they call it laser speckle imaging. So basically, both are underlying principle is to measure the speckles and try to reconstruct. Right. So again, we can come up with the forward model, which is the diffusion equation, but there is an added term here to account for this movement. So I'm not going to the details. So I'll tell you an example. So for example, a typical measurement for such an autocorrelation curve is shown on the right side. As a red plot. Now, suppose I'm taking the measurement from a rat. We can see that an alive rat has got a autocorrelation curve looks like this as a gray color. The moment it is dead, this shift to the right, because the blood flow has ceased, and so that the autocorrelation will shift to the right. So from this difference, you can actually quantify the blood flow. I mean, I'm not talking about if it is alive or dead, but I want to quantify the blood flow. So this is how you can interpret these measurements. Again, I told you this particular problem, like speckle contrast. I had given this in one earlier slide. You can see if you calculate this noise, this quantity speckle contrast in this noisy image, you can actually reconstruct some of these blood vessels. All right. So what we do in this area, these are the things that is in the literature. So what we do in this area, we will quickly tell you. What we have done is we have done what is called the last portion of the talk that I have given you, that is what happens when the scatterers move. That is called diffuse correlation spectroscopy. So people were doing diffuse correlation spectroscopy with a lot of very sensitive and very expensive systems. So what we did is we tried to do it with a camera, and we found that it is not trivial. And there are some mathematics involved, and I'm going to skip that. That's called multi-step Walter integral method. We used this particular method, and then we were able to recreate some images. So this is experimental setup. So with the algorithms that we developed, we were able to use a camera to do actually a flow measurement. and we employed it both in phantoms. Phantoms means these are materials which mimics the tissue optical properties. So what we did is we used a pump. We pumped some materials through this tissue mimicking phantoms. We used a camera here. We shined it with a laser, and from the scattered data we were able to find out the autocorrelation you can see on the right side. As the flow is changing, this correlation curve shift to the left. As I told you for the alive and the dead rat, here when the flow changes, this correlation curve shift to the left, and we were able to do it with the camera, and that's our contribution. And we have extended these experiments to blood flow measurements in human adult. So we did the experimental setup is like this. We focus a laser source which is 785 nanometer to the forehead, and the scattered light is being picked up by a camera, and we use our algorithm to see whether we can actually measure the flow. Now, how do you control the flow in the brain? So we have done two tasks. One is voluntary apnea task, where you hold the breath. So when you hold the breath, what happens is the blood flow reduces, and it actually can be measured. And another is quantitative number processing task. So here the idea is that we are the subject will be told to do some subtraction, and then when it do this number processing, the blood flow in the frontal prefrontal cortex will actually change. It is reported before in the literature, so that we can measure. So both of the measurements are in the prefrontal cortex, and you can see the changes here. Associated with this, you can see the autocorrelation shift to the left, because of voluntary apnea, the blood flow ceases to happen. You can see with respect to time, the relative cerebral blood flow with respect to time, and also the autocorrelation function. And similarly for the quantitative number processing task, the blood flow is actually increasing because you are working, and there is a change in the positive direction, and then after the process it actually comes down. So these are reported in the literature I have given in the earlier. So you can contact me in case you are interested in this work. So yeah, I think I am done. So I work in these areas. So as the name suggests, we work both in theory and experiments. Although I call it bioimaging, mostly I work in this medical imaging, not in this in vitro imaging I'm not doing right now. And I would also like to tell that this bioscience and bioengineering department, it accepts students from different background. So the faculties in our department are from very diverse background. There are engineers, doctors, physicists, chemists who are working in the same department. So the students are also from very different backgrounds. We accept students from physics, maths, chemistry, biology, engineering, pharma. So you should have a look at our department and look at the faculty profile, and please encourage students from all these different backgrounds to apply for PhD and MTech MSc programs. And that's it. Yeah, thanks. So any questions, please?
Yes, sir. If you could see the Q&A tab.
Okay, 1 minute.
Beside the chat.
1 minute. Let me.
There are few in the chat box, and there are few questions in the Q&A tab.
So how do I see that? 1 minute.
Just besides the chat symbol, there is a symbol of triangle, square, and circle.
Yeah.
Are you able to see?
Yes.
Yeah. Once you click that, you will get that Q&A.
1 minute. So let me see. Stop. Okay, so first question, I guess maybe if I am missing, you can tell. But what are softwares can be used for reconstruction of diffuse optical tomography? Okay, so the idea is that you can there are some software packages like NIRFAST, NIRFAST, FAST. So NIRFAST is a software developed by Brian Pock's group from I don't know, I forgot the name of one US university. And also now it is being developed further in University of Birmingham. So you just search Google NIRFAST, NIRFAST. So that is one package. And then I don't know, there is something called TOAST. That is an algorithm developed by UCL, University College London, by Professor Simon Ritz Group. TOAST. That also you can try. But if you are okay to spend some time, what you can do is to learn some finite element method and develop your own code. That I suggest you to do that, because then you have a flexibility. So that is not a bad idea if you can spend maybe 1 year on that, but it is worth doing. Now, please elaborate the difference between spectroscopy and tomography. It's a good question. So the idea is that why we call near infrared spectroscopy is that there is a spectrum being involved. You are using, because as I told you, there is I showed you what is called a physiological window. That physiological window is something which tells you what wavelength I should use so that this particular light will be absorbed by certain chromophores, right? So they found that it can be from 632 through 633 to 850 nanometer, and we can use any of these. And there are dual valent methods where since there are we have to find out both oxy and deoxyhemoglobin content. There are two unknowns, so if you need two unknowns, you should have two equations so that you can use one more wavelength. So there are dual valent near infrared spectroscopy, and so the spectrum is involved. What wavelength I am going to use do matter, and that's why we call it spectroscopy. Now, what is tomography? Tomography is nothing but you take a lot of spectroscopy data, put it in an intelligent way to reconstruct the object in terms of spatial domain. So spectroscopy will give you an average value only. It will tell you some numbers. It will give you some numbers in an average sense. If I take a measurement from my head, spectroscopy will reveal you on an average what is happening in a region of interest inside the brain. But if you need actually what is happening as an image, as a three-dimensional image, where, say, for example, what is happening to my blood flow in the prefrontal cortex as an image, then you have to do a tomography. And what is tomography? You take a lot of spectroscopy data, put it in an intelligent way. There is an algorithm for that, which I couldn't cover it in this short span. If you do that, you can actually generate images. So that is a difference. So you take a lot of spectroscopy data, you put it together and do proper algorithm that will give you tomography. That's all the difference, but the underlying principle remains the same. Now, which modality is better for modeling femur-bone fractures? To be honest, I really don't know. I haven't worked on that. Maybe I can look at it and let you know. So please mail me. We can have a look at it. What is the concept of k-space? So concept of k-space is nothing but what I told you earlier. So this X-ray, so for example, in the case of X-ray CT, so okay, let me tell you like this. So you are looking for an object property. Okay, so you have an object and you are looking for an object property. Now, object property can be viewed either in spatial domain or in the Fourier domain. So object property, what is object property? Say, for example, mu of xyz, it is nothing but absorption coefficient distributed in a three-dimensional space. Now, just like how do you take the Fourier transform of a time domain signal, I can take the Fourier transform of the object with respect to spatial domain as well. So if I have a signal s of t, what is the corresponding Fourier transform, which is s of omega, right? S tilde of omega. That the corresponding Fourier variable is omega. Similarly, I can always take the Fourier transform with respect to x, with respect to y, and with respect to z. If I take that particular space, that means you take the Fourier transform of the object, that will give me the the object representation in the three-dimensional Fourier space. That is called the k-space. Now, the good thing about computer tomography is that the projection data, when you take its Fourier transform, that is actually giving you the Fourier transform of the object, two-dimensional or three-dimensional Fourier transform of the object in particular line. That means we are actually getting the data in the k-space, right? Similarly, for MRI, the signal that you are getting is actually the Fourier transform of the object. That means you are getting the Fourier transform of the object, or you are actually getting the data in the k-space. So that is what the concept of k-space. And now you invert it, you will get the, so you are getting a measurement which is actually the Fourier transform of the object or the data in the k-space. Now you invert it, you will get the object. That's the concept of k-space. What are the materials used in phantoms for mimicking optical? So we use, there are different things. This TiO2, titanium dioxide based solid phantoms can be made. Then we can use this intralipid. Intralipid is usually used for liquid phantoms. Glycerol can be added to change the dynamics. You can add Indian ink to change the absorption property. So there are recipes for that. Again, if you can contact me, I can send you recipes how to make this. I can tell you some literatures as well. And this can be made. We have the materials available in India, so it's easy to make. It's not a big deal.
Sir, few questions in Q&A section. Should I read it for you?
Where is that Q&A session?
Sir, just besides chat symbol.
Yeah, I saw that.
Just beside.
Yeah. How to differentiate forward and reverse model. So this was, I was explaining several times. The idea is that the forward model will tell you how the probing wave interacts with the material. So the idea is that we should know the object very well in order to have this. So if the object property is very well known to you, you can predict without doing an experiment how this probing wave is going to behave inside the tissue, right? So that is a forward model. And the inverse model is, given this forward model structure, that means that equation or the relation and the measurement, you have to find out the object property. That is inverse model. That is basically the imaging problem. Why there are two lines in the corners of the image that is reconstructed? Two lines in the corners. Maybe because what I have used is, this is just to depict, I have used what is called the Im rotations in the MATLAB. So that will create interpolation errors. That might be the reason why there was a circle around it. I'm not sure if that is what you mean. I'm not sure if it is in the X-ray CT or in some other reconstruction. So that may be the reason. I'm not sure about it. Yeah, by filtered back projection. Yeah. So let me see. Yeah. So this, yeah, I think that it's a rotation problem. So what I did is, I used this Im rotation because the image is being rotated instead of actually doing interpolation at different theta. That's a trick that we use to demonstrate. So if so that particular problem can create the interpolation errors. So that may be the reason why there is a I think it's actually a circle, not a straight line. In material science, we find that at times different techniques could give diametrically opposite results. For example, depending on contrast, I could be looking at RNA or protein in a virus. How do you handle such situations? Medical diagnosis of a disease? My question is clear. I do not understand, and I am not. I don't know. I don't know exactly how to.
Sorry, can I repeat the question?
Yeah, sure, please.
No, see what happens. Let's say if I have a particle having core cell structure. So inside it is a different material. Outside it is a different material.
Okay.
Now when I do some experiments, now some experiment may look only the inner part of the particle, and some other experiment may look at the outer part of the particle. So that means one experiment I may end up saying it is a hollow sphere, and in the other experiment I may be saying it is a solid sphere but of a smaller size. So I mean, the same, we are looking at the same thing, but two different techniques give different results. I mean, like that elephant problem, elephant problem. So that means depending on how you look at it, you get different results. So this one, in material science, it is very common, such things happening. And then we advise that you should do experiment, several different techniques to look at the sample to get a real picture. Now, whether same kind of thing happens in medical diagnosis.
Yes, actually, now I got the points. Okay, so as you have said, it's very true. It's a problem. So sometimes, so for example, I can tell you one example. So when we take the measurements from the human brain, right, in the front forehead, and we are trying to measure the blood flow. Now the question is, which blood flow are you looking at? Are you looking at the blood flow from the skin, or are you getting the blood flow from the cortex? We don't know. So this is again, so it's a shadowing problem. So if there is something that you want to find out is sitting inside, but the data is getting collected from everywhere. So from now, when you try to measure it, which one is giving the data, we have to differentiate, right? So basically tomography will help you to do that because it will give me a spatial distribution of the object that you are looking at. So you have to basically get more data. You have to put more probing waves inside it, get data from get data for each sources, and try to put it together and try to create a spatial information that may solve this problem. But again,
or I could be using two different radiation. Let's say one radiation which can penetrate or one which will not penetrate, and so I can distinguish the two situations. See, one is which. So that kind of thing I could be pressed.
In fact, if you look at diffuse optics, what they do is if you put a source and the detector nearby, the penetration depth will be shallower. But if you put a source and detector further away, the penetration will be deeper. So
Right.
if you put several sources and detectors at different distances, we are going to get the data from different layers of the tissue, and that's how we do tomography.
Okay.
So there, yeah.
One small extension question. See, when we are doing radiography, X-ray radiography, so image we are getting it of the bone. Now, since now image analysis procedures have may advanced a lot, can I measure the density of bone from this X-ray radiography? Because the image will be, I mean, the shadow, the intensity of the shadow will depend on what is the density of the bone.
Okay.
So can I get that kind of information from X-ray radiography?
I don't know. So the problem is I have never worked with the X-ray radiography in real situations. So I don't have any idea right now. I have to look at the literature. So sorry, I cannot
No, but
be.
anyway, fine. Thank you. Thank you.
Thanks. Thank you, sir. Yeah. So I will just see if any other questions, if possible. For any given tissue example, won't there be a change in the value mu due to heterogeneity of the tissue? Can that variation be included in the radiation at angles? Yeah, so the idea is that any variations in the tissue property is being picked up by the data being collected at different angles, right? So that is possible. So I think heterogeneity of the tissue will be picked up by the data, and when you reconstruct it, it can be reconstructed. So that is possible. So we have to get the data at different angles. Yes, I hope that's answer. I'm not sure if it is a different question. Anyway, yeah. So I think these are the.
Sir, lastly, means I would like to just request you to quickly let us all know about the potential applications. Like you have covered many ways in which we can go for biomedical applications. Can you quickly just summarize or list up some of the potential applications, like what kind of diagnosis, what kind of diseases can be dealt with?
Okay, see, the idea is that my expertise lies in this NAR spectroscopy. The problem is it's not very easy to tell from different imaging modalities, because I have spent almost all of my career till now in NAR spectroscopy and still don't know many things about it. So there are experts on each imaging modalities. From my field, if you look at the near infrared spectroscopy, the potential applications are something like cancer imaging, of course. So every time when tumor develops, there will be more blood vessels being picked up there, right? So that creates a lot of tissue oxygen content being changed locally. So that can be imaged, and that will give an idea about the cancer. So it is being applied to thyroid imaging, then breast cancer, of course. These are the, and then we can use this for stroke imaging for rehabilitation purpose. Then you can use it for clinical studies, like cognitive studies and all, where they use FNARS type of, so functional activation. So how to image the functional activation of brain. So that is called FNARS. So these are the some other. Then people have used it for arthritis, looking at the bone structures. So skin cancer. Then if you use OCT, optical coherence tomography, you can use it for eye imaging, right? So these are some other applications that I have seen. And laser spectral imaging can be used for, again, for skin related issues, wound healing, like that. So these are the applications usually people do. So my lab, we are trying to concentrate on brain imaging. Yeah.
Okay. Yes, sir. As you have mentioned that versatile people you means you are having in your department, and I feel that is the beauty of having a research in a multidisciplinary field.
Yes. So this is something I would like to tell. Like, so there are several different people. So if you look at my background, I am from engineering background. I have nothing to do with biology, to be honest. My knowledge in biology is much less. But my expertise is in biomedical engineering. but more weightage towards math, physics, and maths, and the engineering aspects, right? So I'm able to work in this department, and there are people like me, and there are people who are chemists. There are doctors with MBBS degree. People are working. Of course, they have a doctorate as well, but their basic degree is in medicine. So the different types of faculties are there, and they recruit people from diverse background as well. So from physics to maths to pharmacy to biotechnology, I don't know. So any branch, you can find somebody who is working in our department. So yeah.
I would like to convey you, sir. I'm happy to convey you that we have also invited people from Hinduja Hospital and Tata Memorial Center to give some sessions.
Yeah, sure.
And
So I think
also,
we are running late. Yeah.
Okay. Yeah.
No,
So
I'm just asking.
can you stop presenting so that I can share?
Sure. Yeah, I will do that.
And just I will conclude in 2 minutes.
Yeah, please.
So I would like to thank Dr. Hari Varma for covering many, rather I would say new keywords which many of us have not heard and gone through while working in the area of biomedical engineering and applications. So many a times we just deal with biomedical imaging and signal processing kind of stuff. But then having gone through your talk on session today, a lot of new keywords and a lot of new mathematical tools we have come across which can be applicable in this particular area. So I would really like to thank Dr. Hari Varma, and I request you to please accept a virtual token of gratitude from S.P.I.T, Sardar Patel Institute of Technology.
Sure. Thanks a lot. So thanks for calling for this program. So to be honest, this is my first program in an FDP. So I was not very sure what to present, but it looks, I think from the feedback, now I know what all things will be expected. Okay, thank you very much. So I should not, yeah. So
yes,
yeah, you please proceed. Yeah, thank you.
Thank
Yeah.
you, sir. Okay, so we have our next speaker joined with us. Welcome, Pinto sir.
Thank you, Amol.
We also have Santoshi Nagaonkar sir, Dr. Santoshi Nagaonkar, joined with us. Welcome, sir.
Thank you.
Yes, so we have just now done with our earlier session. So we will wait for 5 minutes. Is it okay?
Sure.
Yeah, so we'll start within 5 minutes. So I request all the participants that please be here and come back in 5 minutes. Meanwhile, I would like to convey to you, sir, that we have most of them participants who are faculty from various engineering institutes, and their domain of interest obviously lies the biomedical engineering and applications. So
sure.
some of them are from biotechnology also. Some of them are from pharmaceutics also.
Sure.
But most of them are from engineering backgrounds. So we too have a variety of participants. So that is a good aspect.
How do I share my screen? I just click on present now, is it?
Yes, you have to click on present now. We'll just have your introduction. Okay. Professor Milind Paraya will take over.
Sure.
He will introduce you to all of us, and then you can go ahead.
Sure, sounds good.
Professor Milind.
Hello.
Sir. Please take over. You can share your screen.
Sir, are you sharing the PPT?
No, I have stopped. Acha, okay. Should I share the
Yeah, you share. Yes. You
okay,
share.
I will share the PPT. You can take over. Is it visible?